Hello there, and welcome to Software Development with Mikko from Victory Foundations. Today we're continuing our progress with Utopia Terra module. If you don't know what I'm talking about, if you don't know about Utopia Terra module, I recommend first checking this video over here, where we started developing a grid-based algorithm for converting these GPS locations into vector-based locations. Today we're moving to the testing phase, and we might be doing some finalization on the models we did last time. So let me just share the screen real quickly, and let's see. So we want to test our GPS, and let's recap just quickly what we're doing. So we're working on the Terra module from Utopia, which is my open source library. And we're taking GPS coordinates from like this, whatever system and converting them into a 2D vector-based system. Might be a 3D as well if we add altitude information to the mixture. So we created this algorithm that creates this conversion based on a very simple grid-based system. And we added some models last time, but we haven't tested anything. So it might be working, might not be working at all. So this time we really need to get on the testing phase. But here's the question of how do we test this? So we need to design that first. And how are we gonna do that actually? Well, at least we need some input. And like I mentioned in the earlier video, it's pretty hard to test this GPS stuff or write a unit test for this because the data is pretty it's hard to predict what exactly is the correct answer. You kind of see it in a visual test the best, for which you need like real life GPS input. But we at least know some things. For example, we know that the 0-degree latitude is at the equator, and we know certain things about about longitude as well. But basically we want to test first of all our earlier problem that latitude and longitude are kind of they're perpendicular to each other, and that we have certain length of distance traveled, at least on the latitude lines. So here we had like 1 degree of travel equal like 100.0 units of distance, just arbitrary unit of distance. Which brings to my mind, let's just check if we had here globe vector radius. Okay, yeah. Well, here we are immediately faced with a problem that earlier we defined this globe vector radius as 10,000 units of length, and then we changed the distance unit to measure like degrees of travel. So these are obviously incompatible with each other. So we need to either redefine the unit distance or to find a reasonable value for this globe vector radius. Yeah, that's gonna be interesting, although it's not necessarily problematic. Yeah, now that I come to think of it, this might not be a problem because the unit distance is resolved from the vector radius. So I don't know, might work. But anyway, we can at least on the paper side of things, we can at least calculate what's the distance of travel on this 90-degree arc when we know the R. And you know, we just saw that the R is 10,000.0 vector units. So the radius should be, if the whole circle is 2 pi r, sorry, big R, then this 1/4 of a circle should be pi divided by 2r, half pi r, however you say that. So that we can test. At least we can test if we're getting even close to that, or if our assumptions are correct. And we can test with simple, like transforming this 1 degree of travel into this. Actually, this goes to x. Yeah. Anyway, so let's get on with testing. So let's start by writing a new test. So for that we have the test folder here, create area test. Yeah, that was more complex than it needed to be. Create test world view. Okay. 0.0.1. Now, I wonder if we have a test context available. Context. Yeah. So we can, from here we get all sorts of like execution context and other like global constants. Then we need well, obviously we first need the grid. So let's do that first. Implicit grid. Grid area equals new area. Let's just define the origin as the like 0, 0 latitude longitude coordinates, which matches Greenwich, England, and at the equator. So then we need to make some measurements or get some points. So let's first get the origin equals create surface point at vector 2D 0.0. So this should match that location because it's 0.0. It's at the origin, we defined earlier. Let's just make this private. Doesn't matter too much, but you know. Then we will need some other measurements. Let's try first the This is important measurement because this should match 100 units of vector distance along the x-axis. So create surface point. We have latitude of rotation. Well, let's go north actually, or let's go north. So north degrees 1.0. Yeah. And then we have the longitude. Oops, let's close this one so we can see better. Longitude is just angle 0. Okay, this should work. Yeah. And what else? Well, let's just make the reverse as well. And then let's add like 1 degree of travel along the longitude. So say east. Rotation 0 and east degrees 1.0 to angle, I guess. Yeah. So with this I'll just change quickly this cropping. I don't necessarily like it. Anyway, with these models we have nice, like, we can write east and north and south instead of having to figure out which direction was positive, which was negative, and that sort of thing. So that's what I like about this Terra library. It makes things not necessarily simple, but at least like human understandable. So next, let's test what kind of output do we get when we transform these into vectors and latitude longitude coordinates. So at least the origin should have a latitude longitude coordinate of 0, 0. That should be very clear. 1 degree latitude north should have 1 degree latitude north vector should be something around north. Now again, here we encountered the problem, like, was north down or was it up? Let's just say it's minus. It's probably minus because the axis goes from north to south, I think, but we might be wrong. So minus 100.0 and degree. Vector should be, it should be pretty obvious, but who knows? 100.0. And let's just start by printing these. So equals because then we can at least observe what's going on. And here we want the vector forms. So if you can remember, we have 3 forms of points. We have latitude, longitude, which are angle based, like how much the angle has changed from the, according to those lines. And also then we have the point format, which kind of is a bridge between the latitude, longitude and the vector format. And then we have the vector format, which is in this case like 2D vector. And we have a 3D vector as well when we add altitude information. So those are the 3 forms of representation when using Terra. Anyway, let's print this last one as well. Longitude east. Okay, so we didn't need to test context, so let's just comment it out. let's see what happens. We most likely will encounter something we didn't expect because we went so long without testing stuff. That's something I need to work on myself, kind of building more discipline in testing and also more understanding in testing. Yeah, right. Because this is interesting. This is really interesting. So we're really not getting anything done here. Okay, don't use this part of the library. It doesn't work. At least not yet. That's kind of funny, you know, because we get like the same value even though we went to opposite directions. And when we go east, we don't get anything. So that's bad. That's really, that's even worse than I thought. But kind of funny at the same time. Anyway, let's figure out what's going on. So first of all, I guess let's really take some time to see what's going on in these methods. So I guess we need to, instead of using those point classes, let's go to the methods themselves. And I think the most important methods here are this lat long to vector, and vector to lat long, and also this one is probably something that's going to mess us up. But let's start with this lat long to vector function and add a lot of printing to see what's going on. So just print everything basically. Converting long to vector. Okay. And let's print relative position equals position, or let's say position relative to origin equals that. Then we have the x equals x. Then east, west, arc length equals west arc length. And then we have converted to latitude travel equals latitude east west travel. And then we have y equals y. I'm not sure if these toString operations work as expected, but hey, we can at least test it to see, and always we can add those. So for now, I guess let's forget about this stuff because it didn't work anyway, and let's just focus on testing the first function. So what we have, latitude, longitude. I guess let's start with this first one. North vector equals here vector, and then the same input, which is 1 degree of travel towards north. Yep, that should probably work, maybe, or at least that should be it. And then I guess let's just print it, although we have it already, but you know, point is to see what's going on. So 1 north, 0 west, that looks good. 0 south, 0 west, that looks good. Okay, we didn't have a rotation to string, so that we need to add. And from this we get x. Yeah, this was basically the value we were checking. So let's first add a toString to this lat long rotation instance so that we can see what's going on there. It will help later as well. So toString. So what do we have in lateral rotation? We have north to south rotation and east to west rotation. So probably the easy way to implement this is to simply say north, south, east, west. And I wonder what those have. So let's see. This doesn't have a toString, so let's add one. So basically we want like x degrees south or x degrees north. So let's do wrap direction. I guess no, not this. Let's do direction. No. Let's do wrap decrease towards, direction. That should be easy. Then east-west rotation. Let's have the same thing. It's kind of copy-paste, as you can see from the comment. I already written wet here, which means write everything twice. So this is something we might need to work on, like combining these two classes. This is not necessarily wise to have it like this. Fortunately, these are very simple classes, so the damage is not horrible, but I don't like it. Because right now we're again writing the same thing twice. So we're really... Well, I guess we should just... Yeah, we should just move this over here. And maybe we have it already. I don't know. Let's see. We don't have it, but this is a better place. Because now that gets implemented in both places. So we don't have to write it twice. Nice. Okay. So we have rotation. Yeah, this looks good. So let's try again. One north, 0 west. So that preserves. That's good. But now this mystical 0.57. I guess we need to go look into that next. So create area. And here we're using the latitude rotation to vector length function. So we have the decrease. This should be 1 divided by 1 latitude degree arc length. Oh yeah, okay. Well, here we have identified the first problem, and this is like, this has tripped me up before as well. This should, yeah, let's fix this at once, because this one gets me into trouble continually. So this rotation returns this decrease in always a positive number. And that's bad. So let's rename this to absolute decrease. But because we are dealing with library that's already in use, we cannot just rename it without causing build errors. So we create a copy and do absolute decrease and deprecate this previous version. Please use absolute decrease instead. This, what version of Paradigm are we working on? Let's see. Paradigm, as I mentioned before, is my module for sort of vector calculations and that sort of stuff. So 1.4.1, we might have to move it to 1.5, but since this is only a deprecation, we'll still keep it like that. So what was the class again? Rotation. 1.4.1. Yeah. So now whenever we attempt to use this decrease, we're faced with a warning that says, you know, please use this. So we won't then make as many mistakes when we read absolute decrease instead of reading decrease and assuming that that can be both positive and negative. So that's something, you know, something I've been thinking about, creating an absolute rotation class and then having, maybe we can create this new decrease function later where it can be negative as well. But anyway, or clockwise decrease. Yeah. So let's fix any issues we might have already. So yeah, we already have some in this class. This is absolute decrease here, and then absolute decrease here, and then in color we have absolute decrease. I think I might check what that actually does. It seems like I've already faced some sort of problem here. Towards the specified. Okay, yeah, looks good. And then where was it? I don't know. It's like this. This kind of UI. This, I use this sort of zoomed in UI so that you can see something, but you know, this isn't what not what I'm used to yet. So what do we have? We want the window, view, two windows, fine, yeah. And then we have two places in Terra. Grid area, this was the problem. So clockwise decrease. And then this one is absolute decrease. That's good. So that was that. Then let's go ahead and document this change as well so that we can remember. So remember what's going on, and so that the users of this library can know what's going on. So deprecations. Okay, decrease rotation in favor of absolute decrease slash clockwise decrease, because, well, let's keep the because for later. Anyway, then let's add some nice styling. keep up good documentation whenever you can. So then we go back to the grid area. And yeah, so instead of 100, we get this interesting 1 latitude degree arc length. But shouldn't that be... What the heck is the unit distance function anyway? Let's go and see. Distance that matches vector length of 1. Oh yeah. Yeah. It's a very different thing. So here, because we knew the mean radius, and we have allocated a cloud vector radius to match that. What's going on? At least this comment is wrong. So this unit distance might be like, shouldn't this match, or didn't we plan to have this match like 1 degree of travel, or 0.01 degree of travel along the latitude line? So that for that, this globe vector radius is just BS. Globe vector radius should be, what should it be? Well, we can at least reverse engineer it in a sense. So let's go back to the drawing board. Anyway, okay. So here we are back at the drawing board, so to speak. So let's deal with this vector radius stuff. So here we have the assumed spherical globe, and we have the big R. This we know in real life. I mean, no one has ever measured this, probably. Like, I don't know where they come up with these numbers. But anyway, we know this number, so we can use it. But we have defined that like this little 1 degree. Obviously, this is larger than 1 degree in this picture, but who cares? 1 degree of travel, which we call, let's say, L. This should be 100.0, or whatever we assign it, a vector number. So if that is equals 1 degree of travel in latitude distance or latitude direction, so north to south. So if that's 1, and we know from trigonometry that 2 pi r equals the rim of the circle, then 1 is just 1 divided by 360 times 2 pi r. That's kind of funny, we're mixing radians and degrees, but I guess that's how it goes. Radians is the mathematics stuff, and degrees is forced by the latitude, longitude. Wonder why they didn't use radians instead. Yeah, so what did I just say? 1 degree equals okay, so looks good to me. Let's work with that. So first, instead of defining this globe vector radius like so, we need to define what's like 1 degree latitude vector length. Arc. nice name again, but that's how it is. let's say this is 100. We can change it now because we have actual like good value here. We can change it whenever we want to. And next, let's see. So the cloud vector radius now is, that's the 360 times this value. So 60 times 1 degree. No, radius. Okay. That's different than the circumference. But let's still add a value for the circumference as well. While we're at it, globe vector circumference equals 3 times 60. And then from this circumference we get the radius, which was basically, if circumference is 2 pi r, then r is circumference divided by 2 pi. So globe vector circumference divided by 2 pi times 2. Okay. So now we have a real globe vector radius value. Then 1 latitude degree arc length in what unit vector space? We have it here. So I guess we just remove this and fix the mess. And do we need anything else? Unit distance. So unit distance should be based on converting this distance to we want it to match, be based on this. But as we mentioned, we know the mean radius. Basically, we need the distance to vector modifier. So we need to calculate. Man, I don't like this. I wonder, does this work? Yeah, might work. Let's see. At least we should be getting different numbers now. Nice. Sounds in the neighborhood. That's what I have to deal with. Anyway, x minus 1.0, that looks exactly what we want it to look like. And y, 0. So nice, really nice. Thank God. Thank you, Jesus. So let's continue with the testing. Next, we want to check what happens when we go south and when we go east and west. So south vector is great. Blum, 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 blum. Just copy, go south. Then we have east vector. I mean, we're repeating the same thing 4 times, but this is testing. It's not like so horrible even. Well, you tell me in the comments, is this like horribly bad to copy paste in tests? Or should we have like a function to do this for us 4 times? Anyway, share your thoughts in the comments. At least I feel a little bit bad when like writing, copy pasting stuff all the time. But I know, like, I don't think you want to watch me create like very unnecessary functions either. So let's try this. And east and west, we're dealing with the kind of simulation approximation. That's something you can say. Because we're taking something from the latitude and converting it to longitude. But because at this origin, we're at the equator, in this system it should have the same circumference as the latitude side. So we actually should be getting, like, east should be, I think, well, I can't remember if it's plus or minus, but it should be plus or minus 1, and this should be the opposite, plus or minus 1. So let's see. Really happy if this works. So here's the north. Let me check. South 1.0, exactly what we wanted it to be. 1 degree east. And here we have our first, you know, kind of like not so, how do you say it? It's not exact. So x is 0, okay. East-west arc length 0. That's not good. So here is our first problematic line. So that of course transforms to 0. So east-west arc length is the next bug. Let's go back to the grid area and see east-west arc length. So how is this calculated? Position east-west, it should be 1 east arc length over east-west radius at origin. Yeah, we don't know what the east-west radius at origin is, so let's print it. Maybe the problem is there, maybe the problem is in this arc length over function, which, if I remember correctly, I haven't tested, so we might need to test that one as well. But let's first check the radius. So east, west radius and origin dot latitude equals east-west radius at origin. Okay, 1 east-west radius at 0 degrees, 0, 0. Yeah, that's the problem. So why is it a problem? East-west radius at origin is Clove math, east-west radius at latitude. Okay, so might be this function. That would mean we have a problem in our spherical Earth model as well. So good thing we kind of found out a problem. Let's see. Oh yeah, well, this is what I thought. We returned the z first and then the y. And z was the vector height of the latitude level, kind of when measured from the so-called origin or center of Earth. So in the documentation we say that we first return the radius. So that's just a simple programming mistake, I think. So let's see if that fixes anything. This is why it's good to do tests and to do simple tests, because the mistakes can be very simple as well. So -1, +1, 0. Well, we're still having 0. Now I'm a bit disappointed. First. Well, I guess we need to go here. So x, z at latitude, assuming r equals vector radius, yields xc. Well, this is not to like this length direction function. Like I've used this so many times. I don't think this is the problem, but who knows? Latitude angle. Let's latitude angle here as well. Let's see what's going on. Some people like to use a debugger here. I'm for some reason more used to printing stuff. It's easier to read, but to each their own. Oh yes, probably in the beginning. So x equals 5, 7, blah blah. Y 0. Yeah, y should be 0 because that's the, yeah, we have this very wrong here. Okay, so let me show what's going on. Yeah, so what's the xz anyway? We're assuming a circle here. Then we have this is like 0 degrees latitude. This is 90 degrees latitude going north, and this is 45 degrees. Let's say this is our latitude. So we're using the length direction function. We're specifying that length, which is here, length equals r, and direction equals this latitude coordinate, which in this image is like, that is 45 degrees north. So from this you get this vector. This is the lender vector where x is here and y is here. So y shows how high we are on the North Pole and x shows like what's the radius at this level. So if we look at this from kind of a 3D point of view, we have here our little vector. Or let's see, this is like the 0 latitude, this is the 45 degree latitude, this is our nice lender vector. So here we have this returns the little r, which determines the kind of circumference at that level. So the circumference of the east-west ring changes whenever we change our latitude. It's really impractical, you know. Why in the world are we using like an angle-based system that has like changing coordinate systems? I don't know. Why don't we have any better system? Well, maybe we can create one. We are creating a workaround at the moment. So here we had written y and z is like 0 always. So that's obviously wrong. So we should have x was the radius and y was the z value. So we can just return xy. So x, z, x, y. Oops, x, y. Like so. Had a nice function for that anyway. So next, let's fix the imports. I don't like the warnings. So let's try again. Now we see that x is 5 point something, y is 0, y should be 0, and r equals 5, same thing. So, which is basically what we just said, that at the equator, the circumference should be the same as at the poles. You know, assuming a perfect sphere. This is not an oblate spheroid, where things are different. So, next one, nice. Now we have east is positive, like almost 1, and west is also positive. So even more problems, but hey, we're soon running out of problems. This was good. Let's go back to grid area. Y is west. Let's actually look more closely into the input there. So tool windows run. So how is west and east different? One east vector, one west. So relative. One west, one east. Okay. Radius is the same. East-west arc length. Okay, so this is returning the same number, approximately. Even though it should return like the opposite number. So the problem is at east-west arc length over, okay? Y. Oh. Okay. This is another one of those things. Like, I think I thought about this default value when I was writing this, and I was like, is this gonna cause trouble later? Well, we're at the point where it caused trouble. So we really have to think, even like we can fix this easily, just defining the direction, but having this default change when we change the direction of the rotation. No, this is not good. So let's fix this function. First of all, this is a pretty recent function, so it shouldn't be used in many places. So obviously, positive direction default should be like, you know, the positive direction. And we could write like absolute arc length function that specifies this this direction. So let's I guess do that. But we also need to be very careful because right now we're changing the the functionality of this method. So if someone's using this method right now, we're just ruining their day. So is there any way to avoid ruining their day? I'm not sure. I really don't think there is. We just need to make sure we really comment this well. So change the positive direction to rotation direction positive. Let's not even like make any assumptions here that it's clockwise or something. It's just positive direction. Okay. So now we just need to update the comments. Length of node. Default is positive rotation direction, which should be clockwise. Okay, let's check it. Doesn't show clockwise. Maybe clockwise. Now the next time someone reads that, it's easier for them. Okay, and now this we need to move to the absolute version. So let's copy and add absolute arc length over circle radius. Remove this parameter over here, and then use arc length over circle radius and specify our direction. Okay. This comment is unnecessary. This is unnecessary. Remove this negative stuff because it can't be negative. And then here, and the negative. Okay. So that, at least to me, looks better. You know, when we want the arc length, we can just as well call absolute arc length. But actually let's make sure we have, because we had the kind of reverse function here for arc length, but this, let's change this rotation direction positive to match what we have there. Yeah, this has the same default value, so it should be good. So now we need to add comments and change the version as well. My style of naming version is that the first number is for like major updates, like big overhauls when I write the whole library again, kind of things. Second number is everything that causes breaking changes, and the third number is every time I update things without breaking anything, which is a bit rare. So breaking changes rotation dot arc length over blah, full direction, positive direction. It's now clockwise instead of the direction. In order to match previous functionality, you may have to use absolute arc length over distance. Yeah. So as long as people read this, which they might not, they shouldn't run into trouble if they do it early enough, this fix. And I'll justify this to myself by saying that I think I just added this function in like 1.4, I think. Let's see, rotation, arc length, yeah. So maybe not too much damage has been done so far. Anyway, unfortunate that this sort of thing happened, but I'm happy I ran into the problem early enough, and in this sort of controlled environment that could have been pretty bad. So let's try again. We have east, minus 100, west 100. Nice. So east is negative. I guess for you it's east is negative and west is positive, except that, yeah. I don't know if is that how it's supposed to be, by the way. Let's check. East, west. Did we choose to make positive direction west? We did. Oh yeah. The logic here was that the sun goes east to west, so positive direction according to time when observed from the Earth is east to west. So that makes sense. Yeah. So okay, now we have now everything has succeeded so far. I guess we could, like, instead of printing, let's add the assertions so that we can repeat this test later and have it fail here if it doesn't work. North vector something around minus 1.0. Vector should be 1.0. East vector should be 0.0 minus 1. And west should be 0.01. Okay. So I think we can say that this lat long to vector function works now. And let's go ahead and test this other way around, and here we might, well, are we still gonna repeat ourselves? I think we might. So north lat long is vector to lat long. 2D equals 1.0 and west equals 3. Vector to that long. Vector to the 0.0. Okay. Then let's add the assertions again. So much syntax going on, but anyway, so that would be north degrees 1.0. And let's actually let's add default values so that we don't have to repeat ourselves. Angle 0 here, and then rotation 0 here. I like Scala because it has this. Well, I like it for many reasons, but one reason I like it is support for default values. Yeah, it shouldn't break anything. Let's add default equals 0. Default equals 0. If someone can tell me why this keeps breaking, this it always changes the indentation, let me know. Anyway, so this works. This is just south. This. And we need to use the approximately equals because there are always these. What do you call it? Like rounding errors and that sort of things. So import equals extensions. This is to enable us to use this. Okay, this is to break us from using anything, I guess. Let's see if lat long even extends. Yeah, it doesn't extend. So extends approx equals approx self equals in this case. Approx self. Come on. However, approx equals approx self equals. I wonder why I didn't find. Oh, because I used extends and not with. So approx self equals that long. Okay. This adds support for this kind of almost equals function. But in order for that to work, we need to add these two functions. So self is this equals function, well, that we need to add. So implicit all approx equals function equals AB. And here we're just using this lambda syntax. We accept two instances of latitude, longitude, and we need to return a boolean whether they're almost equal or not. So let's see. These consist of latitude, which is rotation, and longitude, which is angle. I think both should support this, this almost equals comparison. So let's see. A dot latitude equals B dot latitude and A dot longitude kind of equals B dot longitude. Okay. Yeah. Good. We don't need this we don't need them, but let's keep them anyway. So quality function that allows for some inaccuracy, I guess. I wonder how much inaccuracy that allows for, by the way, because when we're dealing in latitude and longitude, it's very, very precise. But it shouldn't be like, because we can, well, let's not make this implicit at least, because that can cause trouble. Because in latitude, longitude, we don't necessarily want to have too much inaccuracy by default. So for now, let's add this like so. We might have to use a different function because the inaccuracy in these functions might be too large. But anyway, back to testing. Yeah, so this works. These don't. No, this is. Let's see if that's just an old problem. It's kind of not disappearing. Okay. So what does it say? Has dimensions and has dimensions. Can it be applied? Why? Come on. Just we just had it. Like, are we still importing that? No. It broke when I imported the extensions. Now it's just annoying. Let's try doing it again. And then removing it. Maybe. Yeah. That was kind of futile. So. Oh, well. Because it's vector, not vector 2D. Yeah. That's a bit confusing. Vector is one of Scala's kind of built-in classes, while vector 2D is of my own making. So kind of easy to mix those up. So east, west, east, west. Yeah, this. Well, maybe it's. Oh, yeah, we're missing one assertion here. So it's not north, first of all. Longitude equals east degrees. Then we have east here. Then assert. Let's copy this. West equals west. Okay. Let's try our luck whether we get it first time around or not. Oh wow, we got it. Nice. Lucky. Okay, well now we have thoroughly, more or less thoroughly tested these. I think we should test for the special use cases, or special normal use cases, I guess, where we're not at the equator. I'm just thinking like how can we predict the results? Well, at least let's implicit. It's bad. It doesn't hurt. Doesn't matter. Let's try create 2 equals area. This is a that long north degrees 45 degrees north. Should be a nice number. And then let's print some vectors here. So to long vector origin first, then vector. We have, let's say, actually, origin 2, of course, this. Origin 2. I guess this is necessary. Say origin 2 plus north degrees 1.0, and then oops, the same thing, but this time we go west. Okay, let's start with those 2 tests, and actually, let's not first remove our printing because we might use plus. Compass rotation, lateral rotation can be applied to rotation. Okay, so this for some reason is returning rotation. Should return, you know, the right type of rotation. So compass direction. You have some sort of compass rotation class already. We do. Axis rotation. Yeah, I think we can at least return that. So where were we? Grid area test. Here. So instead of rotation, we return compass rotation, and we add the axis, which should be this. Yeah, no direction. Compass axis. Come on. Oh, axis. Okay. Sorry for being unclear. This is pretty basic stuff. I'm just refactoring, changing the return type so that it's more specific. We don't want to use rotation when we have sort of compass rotation available to us. Then distance we have compass travel. So that's good. Of course, we might have to mark that in the documentation, but this Terra module is like still kind of work in progress, so not gonna worry too much about breaking things. So yeah, let's run the test. So okay, that last value at least looks reasonable. Of 45 north, 1 west. Let's see. 46 north, 0 west should be, yeah, almost 1 with some rounding errors going on. That's good. That's very good. Then when you go 1 west, it's positive, and it's 0.7. So it's not quite 1 because again the circumference is smaller. So it makes sense. I don't know if this is exactly the right number. Again, it's pretty hard to test. We could, I guess we can add, let's add for fun. What happens if we have this to lat long blah blah. We have lat long of like north 90 degrees north. So that should be like at the pole. So let's add that at the end. That should be 0. Travel by, yeah, 45. 45. Well, that is 45 degrees travel, but shouldn't be like in hundreds. Yeah, actually. Well, I mean, the current thing makes sense. Like 1 degree equals 1 unit. I'm just a bit worried whether we're gonna get some large rounding errors if we use such small values. So let's go back to the grid area and inspect this further. So here we have declared that this is like 100. Obviously, right now it's 1, so something's wrong. 100 times, yeah, should be fine. Globe vector circumference. This should be fine. It's probably this. Mean radius. So here we have, yeah, I think we need to divide this by 1, like so. Oops. Well, I would like to keep this one line. I wonder why we're having indentation problems here, but can't help it. So we added this division. Can we justify it somehow, or is it just random attempts? Let's see. This is like, now we have 1 degree of travel, but then we need to convert that 1 degree of travel into vector length. Yeah, that's good. So let's see again. Of course, our tests are gonna break. Okay, that's not good. Nothing changed. Okay, wonder if this applies. I mean, obviously it should change something when we divide something by 100, but why is it not changing? Huh. Unit distance. Well, unit distance is not used anywhere, so that makes sense why it's breaking. So here, back here, X and y. Okay, yeah, it's factoring function. So yeah, here we have it's hard coded times 100, which is, I mean, shouldn't have this here anymore. So we have clockwise decrease divided by, shouldn't this be like divided by 360 times that? Yeah, we should be. I think. Should look something like this. So here we should be doing the opposite. So we divide by this. And then multiply it by 360. And then transform it into rotation. Okay. So divide, multiply, multiply, divide. Should be in the right order. Okay. Now things should break, right? Yeah, good. Except that, nope. This 360 is probably bad. Decrease. Okay. If 1 degree equals whatever, we don't want this, basically. We don't want this. Next. Breaks, good. Yes, 100. So we could just, I think we might even want to expose this. So the vector length is this covered by 1 degree travel along the latitude circle, I guess, southward. Do we want to make it 100, 1000, 10,000? Let's see. What's 100 times? I guess we need the calculator here. So 100 times 360, 36,000. That's not too much. Maybe we want to make it nice million, you know. So let's 10,000 times 360. Yeah, I like that number. So 10,000. Now we should have larger numbers, which should mean like less rounding errors when we're dealing with very small numbers. And usually when we are dealing with travel along the like angular travel on Earth, according to the latitude longitude system, the differences are pretty minuscule. So they should be a lot better, but our numbers should be pretty bad. So let's just use all unit equals grid 1 degree. And of course, actually, because this is a hard-coded value, you can just move it into the object. We don't have to to have it in every instance separately. So let's do that. Let's move it here. Then these as well. These are kind of fixed values. So I think that's good for now. Let's just expose these as well publicly. So documentation, important. Assume circumference of the Earth in vector units, distance units, I guess. Circumference, yeah. The assumed radius of the Earth sphere. Mean radius for a sphere in vector distance units. We assume this because we cannot verify this, plus this model just, models and assumption anyway. So let's just import all those things here. Okay. And now in our grid test, you can just use grid area dot something and replace every one with a unit. Well, maybe we should not be doing this manually. Yeah, a bit faster this way. Okay. Let's try again. Lots of trial and error, as you can see. I hope you're enjoying. I don't think testing is the most exciting thing ever. If you're watching, good for you. Thank you very much for watching. And share with me in the comments, what do you find exciting about this? So right now we're running into trouble because the rounding errors are getting really bad. Like instead of 1 degree we have 0.999 degrees, which transforms into a lot. Like instead of 10,000 it's 9999. Well, I mean, it shouldn't be too much of a difference anyway. It just looks big. That's how they get you in marketing as well. Looks so big of a difference, even though it's just point something. So where are we failing now? Failing at this line here. So, oh, okay, yeah. No wonder we are failing, because when no. Yeah, this decrease should still be like 1.0. So east decrease, west decrease. Do we have any other decrease here? Decrease this decrease 45. Yeah, kind of went too far with the replace operation there. Okay, next attempt. That's good with the unit tests, is that you can run them so quickly and so many times. And whenever I change something, I can still kind of keep things going. So minus 45 is good. 0 exactly as it should be, except that we're not moving west or east. So let's add that. East degrees, like I don't know, 45 degrees east should still yield. Oh, oops, not here. Let's take this and move it here. So that should still have the y coordinate of 0. I don't like this error here. So we, oh man, yeah. Oh yeah, it's because basically because the origin is, we're using the origins radius. So this is an example of one of those. If you use far enough values, you get pretty bad errors. That's part of the system. We might change that at some point, but right now it's part of the system. So need to import these again. And here, instead of 100, we should have unit. I think. Yeah. Let's see if that runs. Everything runs. Okay, so now let's just remove these tests for now. Sorry, prints. So we don't have to face them every single time. And we could be adding some tests for the 3D points, but I think we're running already. We have gone on for a very long time, so let's have a break here and come back later maybe. I hope you enjoyed watching this episode of software development. If you have any ideas, feedback, improvements, please share in the comments. If you are interested in using Utopia Terra for some of your GPS projects, please go ahead and visit my GitHub account. You can find this under Utopia Scala project. And what else? Please check for other software I have available, other open source software, and let's keep in touch. See you then.